Now let's see here. Actually, I still have to get my thing open here. Let's see. All right, I'm going to try sharing the entire screen.
Yep.
Let's see if that works.
Yep, you just have to click on your PowerPoint.
Okay.
I can see it.
Now, how do I minimize this?
Minimize.
Oh. Look at the slideshow for your PowerPoint and see what happens.
Then it will be only you. You can also do
Okay,
this.
yeah.
There we go. That's better.
Yeah.
Okay, so last year, some of you who were here may remember that I had done a talk on basically the same topic, where a reasonably new kind of instrument in astronomy over the last 25 years or so, which is called an integral field spectrograph, or simply integral field unit. And last year, well, let me give you the backgrounds on these first. What does this do? The basic idea is that it combines imaging and spectroscopy, so that you've got a picture, but each pixel in the image has a spectrum associated with it. So you have 3 dimensions of data, X and Y on the field of view, and then your Z-axis is your spectral axis there. This allows you to do a few different things. One is you can take a look at what the scene looks like, your target looks like at any wavelength or range of wavelengths, such as a filter that you want, a particular spectral line, or a comparison of them. Or you can take regions of the image and find out what their spectra are. As an example here, this is using the KEK Cosmic Web Imager. We had a galaxy cluster in this that we took some data with. And because we had found multiple gravitational lenses, and I don't have my pointer sticking here, but the 3 circled areas going up the middle are three images of the same distant lensed galaxy. But on the lower right, this is, you see the bright area here. This is the so-called image. And the KEK Cosmic Web Imager, at least in the settings that we put it at, was more spectroscopy oriented and less imaging oriented. But it gives you spatial information as to where this is. So these are the pixels of the image. 2 galaxies there, 1 up there, and then this bright area here. This is actually a serendipitous discovery of a Lyman alpha blob, to use the technical term, which is a glowing region of Lyman alpha emission from hydrogen gas, although we don't always know exactly what the phenomenon is that causes it. But as I move the region, this is in the DS9 imaging program, move the region from the top to the bottom of that blob, you'll see the spectral line shifted over here well into the 5100 angstroms. You'll see that spectral line shift red to blue and back, or the other way around. Okay, now look as the peak goes on there as I move on down here. So we've got the spatial information along with the spectral there. Okay, but this is not a great imager, at least on the setup that we did. And I think there are a few other settings. Let's see, go on to the next page. There we go. So what can you do with these? Well, a lot of great things then. The archival value coming out from my PhD research was using the Hubble Space Telescope looking at quasars, but I was looking at all archival data. I didn't take any of the original pictures. And so the different people who had proposed them had used a multitude of different filters. There were different redshifts. Nothing was standardized. It was a real mess to try to compare all of these things when people would be using anywhere from near infrared and near ultraviolet filters on that. And it was a real pain. So with an integral field unit, you don't have to worry about that. You take the complete spectrum of your object, all at once, and later on you can go back and you can simulate what it looks like in a green filter or an infrared or whatever, assuming that it's within the range. Let's see here. Extragalactic astronomy, you don't have to worry about getting, if you wanted to have, maybe there's a color term that you need to compare to somebody else's results, but your galaxy is at this different redshift. And the two filters that they use don't really correspond to rest frame filters for the redshift that you're using. You've got to worry about K corrections, these kinds of things, dealing with the spectrum of the galaxy. You don't have to worry about that, again, as long as it's within the range of the spectrum that you've got. You can simulate any filter you want at any redshift. Photometric redshifts work out better. Now, of course, if you've got a very high resolution spectrograph with this, then you can get a spectroscopic redshift. If you have a very low spectroscopic redshift, if you have a very low quality spectrum, you can still get a photometric redshift, but it's better than doing with broadband filters there. And we have a few other things on that there. Active galaxies, which I work on, then of course you can get the spectrum of both the nucleus and of the galaxy. You can find a region where you've got high contrast between those in the spectrum. Galaxy stellar populations, again, even if you don't have the high quality spectrum, you can do it with a low quality spectrum very well, then, or much better than with filters. And ultimately, just don't throw away photons. Do like the X-ray guys do, where they take all the photons in. There's an asterisk on this, because some of the integral field units, like MUs that we were talking about yesterday, really do what we might say multiplex, where they are analyzing all the photons that come in within the range covered by the instruments simultaneously. They don't lose any of them. But what they've got to do is they've got to have for, well, let's take a simple design, simple and easy to understand design. You could take your light focus from the telescope, here's the image plane, and instead of a CCD detector, with the little pixels on that, you just take a bundle of optical fibers, where each fiber captures the light for one pixel. Then, using the fact that these are flexible, you rearrange them, move them around, shine them through the spectrograph, where you've got them now in a column like that. And so each row coming out has a full spectrum. And then you just have a big CCD detector back here that does have to be much bigger. And then it captures all of these. And then in software, hi, good morning, morning. In software, you just slice them up and then you reprocess them that way. Morning, Joseph. Morning. Okay, so the thing is, though, unless you do that, then you do have trade-offs, and you've always got trade-offs of these. You're still not going to be able to do all the photons all the time unless you're slicing it up that way. And doing it that way tends to involve very large pixels, which spatially not a great resolution. So most of these IFUs are designed for spectroscopic resolution rather than imaging resolution. If you do just a 100 by 100 pixel image, that's 10,000 optical fibers, just 100 times 100. And you can see how that's going to grow if you try to get any kind of a large field of view. It's going to be ridiculous. So my original idea was to do this on a budget and with a two-man operation. How about just have the light coming in from the telescope there? We've got a prism to split off, really just as a beam splitter, to split off some of this to go over to the guiding camera. And then the rest of the light comes through. And let's say we just take a normal standard spectrograph with a slit, but we could do, say, 4 multiple slits across. Shine that down to the grating, and yes, I know that my diagram is not really optically correct design, but and then focus it onto the detector, and then each quarter of that detector has got the spectrum of one of those 4 slits. And by doing this, then we can scan across the field of view like doing a drift scan. Hold the telescope fixed, let the skies drift this way, and in the time it takes to drift across, you scan the entire field. And so you do it over time. Now, of course, this means you are throwing away photons in time, but you're not throwing them away with rejection filters like that. So 6 of one, half dozen of the other. All right. So that was what we wound up getting some funding for this. And so the school's giving us $3,000. We would have gotten $1,500, but I brought in an engineering professor, and if we work with two departments, we get twice the amount of money. And it's a good thing that I did, because he came up with a great suggestion last month on this. Here we're using Christian Bull's design. If you go to astrosurf.com, this is kind of high-level amateur astronomy spectroscopy website. And he's been working on these things for at least a couple of decades at this point. And this is one of his implementations of a very standard kind of classical spectrograph. And it's all in French here, and I don't speak French, but luckily the words are kind of easy to understand, like Nikon. All right. Coming in on the upper left there, I'm going to guess that Fente might represent, Fente or whatever, might represent the slit. It's in the right place. I know that the slit is there. I just don't know what the word means. Coming through, we've got a Canon lens, which is acting as a collimator. It hits the grating over here, reflects off of that there. We've got the second lens is acting as a focuser then, and the Aldine is actually a brand name for a CCD. Okay, there's the spectral diagram. But my buddy up in engineering said, hey, wait a second. What if we used a DLP chip? And I asked, what is a DLP chip? And he said, it's the Texas Instruments digital light processing chip, which they use for cinema projectors. It's a micro mirror array. And I thought, well, that sounds kind of interesting. He said, this thing costs about $150. The idea is that DMD is digital mirror device. Okay, but you have an array of microscopic mirrors, and they can tip between two different angles. There is either from the beam line coming in, perpendicular to the chip, it's either about 12 degrees this way or 12 degrees that way. There's nowhere in between. You just get two options. So what does that do you? Well, in a standard DLP projector, you've got your lamp over here. It shines onto the array of the mirrors. And if you have this mirror is on, it reflects it towards the lens that projects it. If the mirror is off, it just goes to a light absorber, just a black body absorber, like that, beam dump. But what if we were to use it in a way where we've got either it goes to the imaging camera or it goes to the spectrograph? And now we can have a virtual slit where we take a column through the image, that's our slit now, divert that over to the spectrograph, the entire rest of the image goes to the imaging camera, which does guidance, and we can just do imaging for that matter. And now we can scan through column by column over time, or multiple columns, depending on how our rating is designed, to get it onto the spectrum bin. This is a video showing as one of these color DLP chips. This is the just a little test image here, and as the color wheel is rotating, you'll see how the individual mirrors go on and off. They actually, in principle, you've only got the two options, on or off. So in black and white, you've got all white or all black. But over time, they flip back and forth. If you want 50% grayscale, it spends 50% of its time on, 50% off, going maybe thousands of times a second. This is done with a stroboscopic camera. If you want it 10% bright, it's 90% of the time off, 10% of the time on, which means that we've also got the ability now to take out bright stars that might be messing with the imaging, that might be overexposing. And instead, we can say, all right, let's set the levels of all these pixels to 10% of their actual brightness. So this is a basic design that comes off of paper. They were testing this out, in fact, actually for the James Webb Space Telescope 20 years ago, as one of the possible camera types. Massimo Roberto and a few others were working on this. And so this is one of their diagrams. So from the standard slit there, collimating, grading, reimager to the CCD, instead you've got to fold the beam a little bit. And you've got to have this as your on direction into it there. And this is their design, the Ritmos, which I forget what it stands for, spectrograph, which was actually used for some testing for one of the James Webb multi-imaging spectrographs. But here, optics coming from the telescope, your digital mirror chip splits it into the imaging CCD and over here to the spectrograph. And then we just do it all in software. And, but what would we go with this for bigger things? I had kind of this idea of doing the balloon, this is the last slide, with doing the balloon flights. I'll be telling you about with my students talk later today. The biologists kind of chickened out of presenting to an astronomy conference at the last minute, so I'll be presenting their talk. But we're doing high altitude balloon flights, and I would like to bring it up to the point of actually getting telescopes on that. And I was mentioning to a friend, and she said, "Oh, you know, you should talk to so-and-so. He had done a low-cost imaging mission. I looked at the low cost, it was SuperVic, which is $5 million. But low cost compared to putting it in space.
Yes.
And this is actually, NASA is actually trying to get a series of these high altitude missions up, long duration. This is 40 days, I believe they flew. And this was a 0.5 meter mirror, which was pretty close to diffraction limited. It's up above, 90-something% of the atmosphere. And this is one of their images that came off. A very stable platform, and with deep imaging. But imagine putting up one of these units where now you can get all the way from the ultraviolet through the infrared without the atmospheric problems there. Okay, that's it for me there.
Anybody have any questions?
So how reflective are those little mirrors, right? Because we worry about reflectivity. This works optically, but the next mission is UVEX. The mission after that is having the world.
Okay.
Right, to do multi-mass spectroscopy, for example, or imaging at the same time. Could you recode these chips, or are this is optical only, or
Yeah.
What's the reflectivity?
So just for those online, the question was about the what range of spectrum do these mirrors work in there, and could that be recoded for a to go into the UV, the infrared, and so on like that? That's a good question. I don't know, and I haven't actually thought to check on that yet, but I should. Because especially if that's one of the advantages of, say, putting it up in space or on a high altitude balloon, really want to make sure that it would work in that range of the spectrum, Yeah, don't know. There are a couple of disadvantages of these. One of them is that because there is a little bit of a gap between the individual mirrors that have room to tip, then you will get some light that hits the substrate and scatters off of it. So you do get a bit of scattered light to deal with. And the second thing is, think about this first, you actually get some diffraction off of the chip because it's in a grid pattern. So considering the size of that there, you're going to wind up with it acts as its own diffraction grating. So those are two things to deal with there. But, well, this is an experiment, so we're going to see how well it works for us right here. But honestly, I knew that there were these, John McEntee at Space Telescope had been working on these ideas back in the 90s, early 2000s for cameras. I didn't realize that this was within the price range of, I could just go and pay cash for one of these things right now. It's that cheap.
Yeah,
And in fact,
150, right? That's what you said. $150.
yeah, right. And so, in fact, Paul Yost, our engineering professor working with me on it, said he just found out that they've got one of these DLP projectors sitting in storage that nobody's using, and the department gave him permission to rip it apart so we can use it as a test bed. So we can get one free, at least for the testing.
So, Tim, how big is your whole apparatus for?
We'll find out.
Oh,
I'm kind of modeling it again on Christian Bull's design here.
That gives me about an idea.
Right.
I mean,
And the thing is, though, that the angle, the splitting angle is about 12 degrees off of the perpendicular to the chip, which means we don't have a lot of room from the focal plane, which means I'm probably going to have to put in I think a Barlow lens would be a focal extender. And if we can get the focal point farther back, then we've got room to split it up here. And I'm still going to have to put some pick-off mirrors like that, fold it back. So I think this is going to wind up growing both backwards and sideways on it.
Yeah, no, the reason why I'm asking, I'm always thinking about, before I was in more thinking about CubeSats, right? If you can put this on a 6U. And
also think about this. There's a guy at Goddard. Actually, he's recently retired, but there's another guy at Goddard he works with. These are some of the people who come to Green Bank I think so. I need to keep in touch with them. But they come up with a carbon fiber mirror to
Mhm.
use for lightweight applications.
Yes.
And they're working, putting it on a CubeSat. But imagine you could have that, that's very lightweight, they're getting it down to the fraction limited surface now. Imagine putting that on where you could have maybe a, multiple mirror segment that folds out of a CubeSat, you could get a larger mirror on.
Right, right. Uh-huh. And all you're carrying mostly is the spectroscopy. I mean, the imaging quality is not that important. So if you have a foldable mirror, okay, your imaging quality, you're not getting HSD quality images, although you're in space, but you still get the light collection.
Mhm.
Yeah.
I'd like to get that carbon fiber mirror on the balloon, where we got
Yes.
room, we got
Yes.
space on it, we just
Yes.
won't have weight.
Yeah, that's always your limiting factor.
Mhm. All right.
Any questions from the audience?
Oh, yeah,
I
sorry.
didn't see any. I was
I
looking
don't see.
online. I did not see any questions come up there. All right. We want to thank Tim. And then up next will be Jay Allen Smith with calibration of large sky surveys online.
Okay. Let's see. Now I just have to figure out how to do this. Let's see. Can I share the screen? Try it.
Stop sharing.
Oh, I can't. Darn.
Yeah,
All right, sorry about that. Let me get that off here.
yeah.
Okay.
Should be.
Oh, are we recording?
Okay.
Okay, good.
Now let me see if I can do this. Share.
Yep, it's good. Yep.
Magic. Okay. Do you all see that?
Okay.
Do you all see my slides?
Yes.
Okay. So I'm going to shift gears and talk a little bit about, excuse me, the how you calibrate these large surveys that you all are using for science. And this will be sort of a historical perspective in some ways, even though it's an area I'm actively working in. So title slide, because everybody needs a title slide. So if you look through history and I'll look at we'll say the modern surveys, the Palomar Sky Survey, the last large photographic survey, the Sloan Digital Sky Survey, which was the first large-scale electronic imaging survey, and then finally the Dark Energy Survey, which is just wrapping up. And I'll talk a little bit about where that goes for LSST purposes. Everything's going to be ground-based because, space-based. What's hard about space-based stuff, just because there's no oxygen, you can't breathe and do things, and there are other issues. And by calibration, I'm also going to consider photometric calibration, even though certainly astrometric calibration is important. And if the survey is spectroscopic or a polarization survey, you have to be able to do that also. So the POS was POS-1, the first epoch, was a 2-plate survey taken essentially the early 1950s. They started in late 1949. They were 99% complete by, I think it was June of 1956, and then finally finished it in 1958. It used the 1.2 meter Schmidt camera or Schmidt telescope camera at Mount Palomar, 1,872 plates that were 6 inches on a slot on a side. So you got 36 square degrees every time you opened the shutter successfully. And these were fairly long exposures, anywhere from, I think they were like four-ish hours, 2 to 4 hours long. They used 2 different plates. The Kodak 103AE plates were the red, and the 103AO plates were the blue plates. And these were the best photographic plate technology that we had developed since, we'll say, the War of Northern Aggression back in the 1800s. Limiting magnitude in the survey is given as 22nd magnitude, but it varies from plate to plate and around the plates. And the general working limits that we used for what was complete throughout the survey was 19.5 in red and about 21.5 in blue. In old days, red plates were not as sensitive as the blue plates. The calibration was done using eventually photomultiplier tubes that would image 2 or 3 or 4 bright stars or relatively bright stars per plate. And you assume the plates were linear, which is not necessarily the case. Most of it was done post-survey, and there were emulsion non-uniformities you had to deal with, where there could be up to a 10, in some cases 20% sensitivity issue around each individual plate. Finally, modern technology started to catch up with them, and in the late 1980s, there was a huge effort made, primarily at the University of Minnesota, to digitize these plates and turn them into ones and zeros, which these modern newfangled computers could use more easily. And in 2001, finally, a catalog of 89 million objects available on the POS survey was made available online. This was a huge step forward for those who were looking for that. This is a typical plate. Bidden et al. in 2010 showed this is not an open cluster after all, this paper, but this is what the typical plates look like. And you see the, star images, you see codec issues with something on the emulsion that wasn't exposed properly. Okay, fast forward to 1990, we'll say 2, I think it was, and the Sloan Digital Sky Survey started coming into existence. This is better entitled "Four Drunks Walk into a Bar," but this is how the survey began at a hotel or at a airport bar in the Chicago O'Hare Airport. And there have been 5 Sloan Digital Sky surveys to date. Number 5 is in work. And so I'm going to look at SDSS 1 and 2, which are the original imaging surveys. The survey itself did imaging and spectroscopy. The idea was we would scan the sky in 5 different filters, near simultaneous photometry, and then process the images. Computers would go through and select target objects for the follow-up spectroscopy as soon as the following month. And we did a lot of different selections based on stars, galaxies, quasars, calibration stars, serendipitous objects, and so on. And the galaxies were divided into 2 or 3 different subcategories we were interested in. We use modern detectors, CCDs. There are 3 different versions of the CCD on the imaging camera versus 1 in the calibration camera. The 5 photometric filters were based on the Tuan Gun UGV RIZ set, and they were reduced back to the monochromatic AB magnitude system. So these are not Vega magnitudes. Generally, the filters are non-overlapping, and they were designed to avoid the strong night sky lines, such as the 5577 angstrom line. This actually saves us something like 50% of the noise value or background noise in each of the images in the filters. So we've already started working on the calibration before we even take the telescope off, or the data off the telescope. The 2.5 meter telescope was used for the survey with a smaller, it started life as a 0.6 meter telescope for calibration, the monitor telescope. There's a lot of stories about that are best told over beer. Long story short, we left the telescope out in the rain overnight. It shrank to a 0.5 meter telescope and changed to a good one. And this was going to be done with a standard. We're going to develop standard stars and reduce all the data to the standard star network. Limiting magnitudes are shown here for the 5 filters at a signal noise of 5 to 1. And the monitor telescope, or later the photometric telescope, would create these calibration secondary patches or calibration patches all around the survey area, which the 2.5 meter survey telescope would then scan over to get the calibration data that they need. And so, like I say, this is a traditional approach. Standard stars would be placed and tie the survey, and we would tie the survey to the standard stars. The science requirements actually got in here, and we started looking at what we need in the end to do the science we needed, and some are listed here. We need 5% in colors in quasars, 4% for galaxy counts, 3% photometry in the selection band for the galaxies, and 1.5% color errors for the stars. And this in turn drove the precision, that last line, of what we needed in the standard stars transferred into the survey field. The remaining uncertainty would be taken up in the transfer from the standard stars in the air mass and uncertainty to go to the calibrate or to the survey objects themselves. So this is, to the best of my knowledge, the first large-scale survey that science actually drove what you needed when you calibrate it, as opposed to most you take the survey data and then calibrate it and see what you get. Okay, this worked well until the first night of data came off the telescope. And at that point in time, a decision was made, well, that's going to be too much work to actually do this the old-fashioned way. So we're going to report all of the magnitudes in the survey in the native, non-standard 2.5-meter system. And that's what's done today. So if you're using Sloan data, it's not standardized. It's uniform, but it's not standardized. So the survey, the calibration stars are placed here on the northern survey. The asterisms show where isolated standard stars are, and the circled ones show fields that also have Landolt photometry from UBVRI. We were able to make use of Landolt's, at this point in time, 30+ years of observing the sky to help create standards. In the southern hemisphere, which has an extension, the open squares are places that we started observing. Again, the circles have Landolt photometry, and the ones at -45 degrees also have Graham's photometry in it, based on the Landolt system. The main survey was described in the York 2000 technical overview article. The standard stars are described in some guy named Smith in 2002. And the difference here is the designated stars that are designated with a prime system are the standard stars that are on the standard star network, which was defined ultimately by the Naval Observatory 40-inch telescope. I'm sorry, the Naval Observatory nautical 1-yard telescope in Flagstaff. They are not the same systems, and they can vary by up to 3% in the ultraviolet, maybe 4%. We still have one little thing we have to narrow down yet. The PT data, which some people like to quote, were internal data only and were never made public. I think you can count on one hand and have fingers left over the total number of people in the world who've ever seen that data. And they're used to tie the standards to the main survey telescope or the main survey via these secondary patches. The issue came up with the 2.5-meter images saturated about R of 14. The PT can only effectively observe to R of about 12 to 12.5 in a reasonable integration time. And it's worse in the ultraviolet end. And so there were some issues here. And so we came up with yet another way to do this. The survey itself, like I say, is tied together at its edges. So every scan overlapped with at least a scan on each side. It's not great to tie the whole survey on, a few stars in a 12 arc-minute band across the sky. But that's what we did at the ecliptic or the galactic poles. Almost all the stripes cross. So we started an Uber calibration where we scanned 90 degrees to the main survey stripes and bin 2x2 or 4x4 and ran it 4 times the exposure. And now suddenly we can get to semi-bright stars, but we tied the entire survey together. And statistically, the survey is flat to within, I think we say 2% across the sky. And, 2%, 0.02 of a magnitude is pretty good for most work. It's the best you can do with all sky photometry of stars. Okay, this is where location of the northern hemisphere secondary patches shown with the black dots in the survey footprint. And then we have in green are the Segway, the SDSS2 secondary patches to tie all that together. And the red are the southern extension patches that go down into some of the southern hemisphere stripes, where southern hemisphere is not all that far south. So that worked well, got a lot of, and a lot of people use the Sloan Digital Sky Survey. And it is turned out that's become the basis of most modern detector or most surveys now. So we jump forward to the Dark Energy Survey, which was done on the 4-meter Blanco telescope at Cerro Tololo with a new camera. Our science requirements drove the entire survey at this point. And so we had a requirement of 2% RMS on all scales in the survey unit with an enhanced goal of 1% over these areas. And uniformity drove the angular galaxy clustering issue, or were driven by angular galaxy clustering. The absolute color had to be known to 0.5% in the colors, G, R, I, and Z, and 1% at Z minus Y. And this is an order of magnitude increase or more stringent over Sloan. And everybody who was working on this said, it's going to be interesting. Absolute flux, we wanted 0.5% in the I band. And this was going to be tied to the Sloan standard BD 174708 until we figured out, that's really horribly placed in the northern hemisphere for a southern hemisphere observatory. And oh yeah, it's a variable, at least a spectroscopic variable. And so we later changed that to C26202, which is one of the Hubble CalSpec stars in the survey field. This would do the zero pointing for the overall filter system by floating the I-band magnitude after the survey was complete. Everything else would be tied across the survey. We had complete overlap from image to image to image, or image tile over the 10 tilings we took in every field. Okay, so the Jar Jar Binks tank up here shows this is in the 5-year COAD. This is not the final version. This is the data release 2, but you see we're within 1.5% uniform or RMS across the sky or across the entire survey footprint. In DR3, which has now come out, we cut these in half or better. So this is a bad image compared to what we're doing now. And the plan was to tie the whole thing together using synthetic photometry of the DA white dwarf stylized here. We take a DA white dwarf, get the magnitudes at each of the 5 filters, and use that to float each of the, originally the one standard star. That was later changed to, we have 40 to 50 well-characterized white dwarfs in the survey footprint, and we're still working on a couple final refinements. The green box shows the AB offset in each of the filters, and we're down. The RMS we like to look at is the statistical RMS. Well, the system RMS is this bottom line, but 0.005 in G minus R, 003 in R minus I. We're off a little bit at I minus Z because of issues with the Z band, and Z minus Y because of issues in the Y band, although it's probably the Z band also. This is also DR2 data. This has been cleaned up for DR3, and it's actually better fit for DR3. So how do we do this? We take our white dwarf stars, we get photometry for them, and we've calibrated the survey with this forward global calibration module, which is our all-encompassing sky calibration system that we use across all 10 pointings, including the coads in the pointings. And then we place our white dwarfs on them, and the dots are the reduced white dwarf magnitude, and the ones we tie to are in this narrow band right across the range there, and the blow up is down here. And the RMS of this is, as you can see, it's fairly low. I don't have the actual number with me right now. And so this is working fairly well. Like I say, DR3, it's getting ready to go to press. We're doing even better than this. All right, so we claim the DES is the best calibrated sky survey ever done by the human race to date. And, you know, that's a bold claim. We have the numbers to back that up, though. DR3, when we're finished, will be done. There are no traditional standard stars in this survey, but we have a plan to create them post-survey using the best data in the field. So if you want to observe in DES filters, you've either got to get down to 20th magnitude to tie things together properly, or you have to wait another couple of years until we get the brighter ones backed out. The internal consistencies are better than any other survey done to date, including pan-stars. Pan-stars, even with the multiple coads and multiple passes, still are not quite what we're touching. And looking ahead to Rubin, when that comes on the sky here in another couple of years, it's going to do even better because we're using what we learned in Sloan, what we learned in Dark Energy Survey, and adding a couple of other techniques in that are still in development but show promise. We probably will cut the DES uncertainties by another factor of 2. And, oh, that's it. I'll open it up to questions.
Are there any online questions or you have, what did you want to?
If there's anybody,
Or did you want to point any?
Oh, I was just thinking that, I don't know, the microphone on that must be kind of facing this way. But,
Or if you want to put it in the chat, that's fine also.
right.
Any questions in the room? Yeah, Tim.
Yeah, Alan, can you hear me okay?
Yeah.
Okay, so my question is on calibration. We're doing these with stars. You're saying you're really not going to get much better than 2%. So it sounds like what you need is a standard laboratory type source that's above the atmosphere.
Yes.
Half kidding about if you could get up some kind of a spacecraft up there, put it on the nighttime side of the Earth, and just have a calibration lamp going. But it actually makes me wonder: could you calibrate off of something like the Hubble Space Telescope passing over? I know it's brief and it's going to be very bright. Would something like that that's reflecting sunlight off of aluminum or off of mylar be something that could be used?
Well, that would be really good, except that's non-uniform in brightness.
Okay.
So, but if you expand that, a project I did work on, we'll say 20 years ago when I was at Los Alamos, was what if we flew a satellite with calibrated LEDs on it that could be observed, say it was in geosynchronous orbit, several of them, and you could observe them from any telescope in the world.
Yeah, right.
And we're working on that. That's coming.
Okay.
We're not there yet. There's another project I haven't talked about. I'm not supposed to yet, the details of it, because we're still building the project up. But that's coming, and it's probably going to take us another 10 years to get where we have good final results.
That's an impressive idea.
Yeah.
Yeah, this is all on point sources. So does it change much if you go to extended sources? Galactic photography being intrinsically harder.
What the what?
The calibration is it's intrinsically harder to do fuzzy stuff. So,
Right. Right, because you can't believe magnitudes that come off of the fuzzy things, right? Yeah. I mean, but we're still improving galaxy photometry as things become. I hate to use the standardized for something that's not standard, but as you standardize what a galaxy is and where you look at the brightness of it, we're now down to where you can actually use uncertainties or errors in galaxy brightness on the order of less than 5% with a well-defined galaxy, as opposed to, say, photographic plates where, well, we think it's this big, but it might be this big, and it's somewhere between 17th and 25th magnitude, depending on what part of the galaxy you survey.
Okay, thank you.
Okay.
Any other in the room or online? Okay. Thanks.
Okay. Let me pop that down.
Thank you. Our next speaker will be Joseph Powell. on nuclear isomeric transition to gamma ray burst and from neutron star mergers.
It's in the bag.
Huh?
The slot is in the bag.
Oh, okay. There's the only one USB port left.
Don't plug anything out.
No.
Is there a clicker?
Like a remote control?
Yeah.
Nope.
Oh, okay.
Let's see, are we showing the screen?
You need to share the
Oh.
screen. I can help you with that if you don't know. Oh, you know, okay,
Think
share
so,
screen.
yeah.
Got it. Yeah, go for it. As many cookies as you want. Take some home, I guess.
We're good. Take some of the lunch.
Well, we have lunch tickets. But if you want more cookies for lunch, sure.
All right. Hello, everyone. My name is Joseph Powell, and I'm from Marshall University. And I'm very excited to share the research that Maria, Dr. Hamilton, and I have been working on for the past couple months. And that is nuclear isomeric transitions and gamma ray bursts from neutron star mergers. So what we're looking at is we're trying to get a better explanation of gamma ray burst spectra. And so current theories explain the spectra in a couple of different ways. And so one of those is relativistic electron synchrotron radiation. And this is from the magnetic fields from the neutron stars being so intense that they can accelerate the electrons into relativistic speeds. And this acceleration causes the electrons to emit synchrotron radiation, and since they're going so fast, it's in the gamma ray spectrum. Another theory is the inverse Compton process, where a high energy electron interacts with a low energy photon, bumping up the photon to a higher energy and reducing the energy of the electron, producing gamma rays. And the final one is internal shock dissipation, which in terms that even I can understand because of how terrible that looks, it's basically shock waves interacting with plasma causes light, and that light can get up into the gamma rays. And so these are the best models that we have today of explaining how gamma ray bursts are formed from neutron star mergers. And they're all lacking one thing: explaining the discrete property of the gamma ray burst. Because every gamma ray burst that we've seen is unique and it's not smooth. It's discrete, just like observing the spectra of an exoplanet or a star. It has discrete points and peaks and valleys. And so that's where our theory comes in. And we are explaining this by using all of these to we can't just completely eliminate the possibility that these are causing gamma rays. Like, yes, of course, we got to consider everything. But to explain the discreteness, we are proposing the de-excitation of nuclear isomers through isomeric transitions might be responsible for causing this discrete property of the gamma ray bursts. And so what are the advantages and disadvantages of isomeric transitions in nuclear isomers? Well, for one, they can explain the prompt emission of gamma ray bursts. When we see a gamma ray burst, especially with the multi-messenger, with the gamma ray and the gravitational wave that we observed, the gamma rays happen very soon after the merger actually happened, which isn't fully explained because with the current theories, it takes time for the photons to break through the initial cloud. And so there's a little bit of conflict there. And so this would help explain the prompt emission. And by explaining the prompt emission, it would also explain short gamma ray bursts, which are already explained. But the important thing is that since the isomeric transitions increase the time of decay for these isotopes, it could also help explain long gamma ray bursts, which are previously unknown how they form. The other important property is that they would explain the discreteness of the gamma ray burst spectrum. So what are some disadvantages to using this theory? So one of them is the lack of isomeric data. All the isomeric data that we have is 100% experimental. They run tests and they excite things and they observe it and they have to do a bunch of tests. But this is only really good for common stable elements. And so heavy unstable isotopes are nearly impossible to figure out if they have isomeric states. And so take francium, for example. It has like half-life of at least less than a minute. I think it's like 12 seconds or something. So what if it has an isomeric state in the nanoseconds and milliseconds? Well, there's going to be tons of isomeric transitions emitting these gamma rays that could be happening within that francium's lifetime. But since it's so unstable, it's hard to actually get data on those isomers. And so that's where the model is kind of lacking. But I really think that the advantages outweigh the disadvantages in this case. And so now, how are we going to gather all of this data, all of this isomeric data, this experimental isomeric data into one place so that we can sort through it and try to make estimates? And so the first step is to make a web app. And so we're going to convert the Atlas of Nuclear Isomers, which is the collection of all isomeric data. And we're going to turn it into an Excel file because at the moment it is in a PDF, turn it into a LaTeX, sort that LaTeX file, and then we can use spaces and tabs as delimiters to put it into Excel. Then we can use Python pandas to grab that data from Excel and use it to graph and make graphs and make data and make assumptions. And we can use Streamlit as a website host for these graphs and for later accessibility. So this is the website. We'll just look at it real quick so that we don't run over too much. But this website has just start without my data. Okay. So it'll have a spectrum of all of the known isomeric transitions in the form of a spectrograph, which will be the first thing that you see. And the second thing that you'll see is a energy versus atomic mass units to just better visualize the data. And on the left, you can see you can filter out any set of data that you want depending on your half-life. And then per half-life, you can go and individually edit and make selections of this data so that you can so that you can gather which isomers you want and exclude the ones that you don't. And then you can download those Excel databases so that you can use them in your research. And at the bottom, we have the solar abundance chart with, and we'll talk about this more in a second. So we've got the web app. Now we can start selecting which isomers we want to use, because our first step is to see which isomers might be possible to see in a gamma ray burst, because it does take time to actually, go through and look at the gamma ray burst. And so, of course, the first isomers we're going to look at is the isomeric transition. Then we're going to look at isomers we're going to look at the isotopes in the R process. And so from iron up to the heaviest elements, they are created in R process. But S process, which is what happens in the fusion of stars and in supernova, that can only create up to bismuth. And they get kind of stuck in this lead bismuth loop. And then once the bismuth gets up to polonium by the slow neutron capture process, it'll decay into lead and it'll stay in that loop. And so the R process can go beyond that, creating heavier elements than bismuth. And that's how we get anything heavier than bismuth. And so we're going to look at those, and we're going to use the estimates that like 50% of in between iron and bismuth are created from the R process, and 100% after bismuth is R process. And so then we're also going to only look at isotopes that are available in our solar system, the ones that are abundant that we can see, because if the heavy elements are being created in these neutron stars, and that's what's going to be creating solar systems, which is what we would be able to observe on Earth. And so by using our solar abundance data of each isotope, we're going to use that to make a rough estimate of how many isomers could be in a neutron star collision. And so making the estimates. First, we're going to estimate the number of baryons in the ejecta. Then we're going to estimate the fraction of total baryons per isotope. Then we're going to estimate the isomers per isotope, and then the number of isomeric transitions per time bin per isomer. And so the estimates. Estimating the ejecta. Got to figure out how much initial mass is going to be ejected from the collision of two neutron stars. And then you have to look at what area that's covering, and that'll help you with the calculations later on. You can use those two things to find the effective mass that will be co-laminated and be, in the energy that's, able to excite atoms into their isomeric state. And then you can convert this mass into number of baryons. This will give you a total number of baryons per neutron star collision. So then we'll take that number of baryons and we're going to take that solar abundance graph that we looked at before. We're going to normalize it. We're going to get weights for each individual isotope. And then we're going to multiply those weights by the number of baryons to spread out the baryons across the solar abundance spectrum, so that each isotope has an estimated amount of baryons that would be possibly being created in these neutron star collisions. So then that will give you the fraction of baryons per isotope. Then to estimate the isomers, you have to calculate the excitation probability of the isomer, because this is related to the total energy of, or it's related to the decay energy of each isomer, and the higher the energy, the more likely it is to form initially. And so you can take that knowledge and create a function of probability that you can multiply to your isomers to separate out your individual isotopes into amounts of isomers. Yeah, and then you get your number of isomers. And so then with your isomeric transitions, because this is what we want to do in the end, is how many gamma rays are being produced, and each isomer is producing, a couple different gamma rays, and so that's the individual isomeric transitions, and so you can use the function of how many initial isomers are there and what their half-life is to create time bins. And these time bins can be, you can go across and make a time spectrum to get almost like a black body curve of emission. And yeah, and so same thing. So now we have the amount of isomeric transitions happening, which is the amount of gamma rays being produced. And so now we need a luminosity. And so first we're going to divide the isomers by their energies, and then we're going to obtain the luminosity. The isomeric transition, we're going to obtain the luminosity from the isomers. Then we're going to divide that luminosity by the effective area from the initial neutron star collision, which is like it's a big cone. And so that will give us the intensity. And so then we can plot the intensity versus the time for each time bin. And these are some of the graphs that we got with some of the most prominent isomers. And we can see that they kind of have a black body S curve, which is what we were looking for. So this is good. This is good. And so this is what we ended up with. And some of the other data that we got, this is the counts per gamma ray energy. And this kind of shows you the discreteness of the spectra. Instead of like, the counts per time, this is the total counts per isomer for the whole spectrum. So this will give you the spectra, and you can see that there's already a discreteness to these graphs. And that a lot of the prominent elements, you can see which ones are there, and it's a lot of the same ones like lead and xenon and zirconium are the main ones. And then here's some more graphs of the isomeric transition spectrum. So just like the one that you saw on the website, just more colorful. I can't make it colorful on Streamlit. And the solar abundance of isotopes, which you also saw earlier. These are all graphs that are in the paper. So for future work, we'd like to obtain the actual data for a real gamma ray burst. We'd like to compare it to the isomeric spectrum. And then we'd like to actually create a real estimate for what elements are being produced and what elements are making these gamma rays in a gamma ray burst. And, of course, using the isomers. And another thing that I'd like to do is create a more interactive and customizable website, because using Streamlit, that's about as customizable as I can make it. Can't really change anything else about it. And then I'd like to fully launch the website and make it publicly available. Because right now you can click on the link and get to it, but you can't actually search it up on the web. So once everything is good, I'd like to be able so that everyone can use the data. All right. Any questions?
Yeah, about the data, the best probably is what you can get is probably Fermi-Lat, right?
Yep.
Yeah, so
Yep.
have you looked into those?
So-
Is the spectral resolution good enough to get the discrete data?
Yeah. The only thing about the Fermi Labs is that you can only run it on Linux or Mac OS. Huh?
Why is that a problem?
Well, because I don't have one. I don't
You
have
can install it on your machine.
Well, I'm working. And so there's the Fermi Lab data that only works on Linux, and then there's Topcat as well. And Topcat is Java software, and I don't know Java yet, and I'm learning it though. So I'm learning Linux and Java, and so that's what I'm doing right now is familiarizing myself. I'm gonna use that flash drive to make a virtual desktop with like Ubuntu or something easy. So
Use the Windows subsystem, that's simple, and it
Okay.
works on every machine.
okay,
Yeah.
sweet, thank you. Awesome.
I know Ben, I had this hand up, right?
Yeah, I'm kind of distracted because I think you Fermi Lat data is just a bits catalog, right?
Yeah.
So you can load that in if you know Python.
Oh, really?
With AstroPy, it's not an issue at all.
Okay.
Oh, yeah, yeah.
Oh, yeah, so you can run it.
The whole fits pack, fits IO. package,
Yeah.
Yeah, I mean.
In AstroPy.
Already has a table. I mean, it was kind of, okay. So the Streamlab app, is that like, it's a website?
Yeah, we can look at that. So this is the Streamlit is a website host. And so like I use the Streamlit package in Python and it makes like a local host website. Just like you would like HTML.
This is sort of like a dashboard. type thing.
Yeah, kind of, yeah.
So is this hosted on one of Maria's computers?
No, this is just hosted by Streamlit. And so
That is, the company is, okay.
yeah, and so if you have the link, you can open it anywhere, even on your phone. And if I don't get on it for too long, I have to like relaunch it. But if I'm the only one that gets on it, then bound to happen. But this is as like detailed as I can get. Like I can kind of change the colors of the background. I can't change the font even. And so and another thing that I want to do is make the data frames like side by side and not just in a big line down the page. I can't do that with Streamlit. So I'd like to learn some like JavaScript, CSS, HTML, like code to actually make like a good solid website. But
It's also a nice marketable skill too, to go along with.
Yes.
exactly. Mhm. Yep.
Completely, yeah, so back to the science question I had, so, you did everything with solar abundances of, elements, right? So some of these neutron stars started much earlier, so they're probably not have a different metal composition or.
Oh yeah, like that. This is just a very rough
No, I
approximation.
think it's great. because
Yeah.
you Start looking at what changes over with metallicity, for example, like, and so you can fit your spectra by different metallicity dates. So,
Okay.
so because wasn't like half the gold is made in the by neutron star.
Yep.
Right?
Yep.
I love teaching that in my one class. Like, well, we thought it was all supernova, but guess what? It's not.
Yep.
So, and so it would be, but this would be a way to see, you can fit the spectrum, and get the information out
Mhm.
of simplicity, and you later you look at the blue optical emission and look at the gas.
If it lines up with the gamma ray data.
Yeah.
Yeah, exactly. Yes.
So I'm gonna say, I'm still impressed by this. When Maria was showing it to me, when y'all were working on this in the paper. I have to admit, I had never heard of nuclear isomers before, and
Is anyone
have-
else?
Sometimes it's the same, what is ISO? It's the math,
So-
right?
So it's
So-
not the chemistry
it's not
isomer.
isotope.
No, it's not an isotope, I know, so. it's
So-
isomer-
so-
It's an excited state of the nucleus.
Oh, it's.
Well, no, it's the metastable excited state.
Okay.
That's what makes it so sorry, I forgot I was Russian. So a isomer is classified by the metastable excited state of the nucleus. So that's why it can explain the long gamma ray bursts, is because some of these isomers have minutes, seconds, years, half-lives of elements that don't usually have half-lives, or most nuclear transitions, like when they get excited, all of these happen almost instantaneously, can't even observe how fast they are.
Right, but
And
they're
so-
beta states, so they live long.
Yes, and so one of them in particular, which was actually one of the reasons why I thought this was so important, is tantalum 180 is only found in nature in its isomeric state. Its ground state is unstable. And they actually use it in medical physics for some imaging technologies, but it's only found in its isomeric state. And so if we were to simulate a neutron star merger, we wouldn't actually obtain any tantalum 180 in our data, because it would have decayed, because we didn't account for its metastable isomeric state. And that isomeric state of tantalum 180 is actually completely stable. It's like 10 to the 9 something years. So not going to ever decay in our lifetime. So, but that was like one particular element that I was like, okay, this is only found in nature in its isomeric state. Just that simple fact alone makes isomers important, at least in like, because we were going to do like actual simulations, but we didn't get to that yet. So
Well, so when Marie was explaining these to me and it's telling me what the word meant, well, that's kind of neat. Why haven't I come across that before? But since it's metastable, in principle, you can get laser activity out of it. So you're predicting that there should be gamma ray lasers involved in these kinds of certain of these gamma ray bursts, neutron star mergers on these. So when looking at Marie, when she was writing up the paper on this, I started checking, and what I get is that this does predict that there should be a polarization direction to these. And I know I don't know enough about gamma ray bursts in general. I don't know if you do switch stuff, but there are some other reasons to expect polarization of gamma ray bursts, right? But there are not very many gamma ray polarimeters that are in space,
That's
right?
correct.
So there's a big gap.
Uh-huh.
This is a great thing to test. There is, I looked up, there is one gamma ray polarimeter that is with a polarimeter that was tested on the Chinese space station, but with a Western team. They did it as a short test, and now they're working, I think this year, on putting up another one that are longer term, more sensitive. So if that data become available, that would be neat. And are there any others at all?
I don't know, honestly.
So this could push some instrumentation and stuff.
So one of the other main reasons that I was like interested in isomers is because of the metastable states, and that's how lasers are formed. And so if we can, increase like the awareness of isomers and people's knowledge about it, and we can get research
We did
into
a
it.
ribbon, we did an isomer awareness ribbon.
Yeah.
There we go.
But that would help get research into nuclear isomers, which could further our like gamma ray technology, and maybe create gamma ray lasers with it, which have not been like, they've tried many times to make gamma ray lasers, and
Because
no one.
shortly.
Yeah, it's so short, so you can't do it the regular way. But because they're metastable, there are complications with the like whole process of like the group excitation and everything, because you have to have like the gamma ray produce, or you have to have like in regular lasers, the regular light excites the next one, excites the next one, excites the next one, and they all raise up at like close around at the same time, and then they decay. But like with gamma rays, a lot of them have multiplicity. And so with the gamma rays with multiplicity actually can't be reabsorbed back into the nucleus, as far as we know. So they might be able to, I'm not really sure. I haven't done the test on it myself because I don't have, gamma ray lasers on my disposal. But there's some issues with like the multipolarity, that's what I meant, not of the gamma rays being produced, not being able to absorb. So that's like one issue for gamma ray lasers.
I did just want to throw in, Alan mentioned online, he says Top Cat is plug and play. The instruction videos are great. So you should be able just to kind of pick that up and run with it.
Yep.
So,
Yep.
Okay, let's thank Joseph again. And then next is Bene Halverda, morphometrics and machine learning.
By the way, Joseph, I still think it's cool that you were just fascinated with nuclear isomers.
Yeah.
You tried to get Maria to find out something to do with it. And she was thinking, what am I gonna find out that I can apply with nuclear isomers?
Yep.
And then stumbles across this.
Mhm.
That is really a cool way that came about.
You could just accept it, so.
Yeah.
All right.
That's probably.
But she was just stretching to find out how she could apply it with the gravitational wave research she does.
Nice. Okay, so do I just play this? And I realize.
By the way, Jerry said a very informative talk on nuclear isomers things.
Thank you.
All right. Yeah, so I'll talk a little bit about science because I have a little bit of an update on this one. I talked about it 3 years ago. I think it was all online, so nobody remembers 2021 anyway, so who cares? But just to give you an idea, this is the Wallaby survey, which uses essentially cameras for their radio telescopes. So you may be surprised to learn that radio telescopes used to have a 1-pixel camera for most of their lives. And now the idea sort of came along like, what happens if we put more than 1 pixel at the focal point? Part of the reason for that is that the computation power that you then need in order to cross-correlate all of those dishes to make synthesis beam was a little bit prohibitive until supercomputers came along. And so I look at galaxy morphology, but I look particularly in H1. And what I mean with H1, it is the 21 centimeter emission line of atomic hydrogen. So nothing excited here. There's literally an electron that can have a spin flip up or down compared with a central proton. That means you can follow the hydrogen around the galaxy anywhere. Because it always will do that little flip. And so as soon as you can see it, at least you know that there's neutral gas. So I've been trying to make a word happen. And it's very much like if you see Mean Girl, either one of the versions, there's like stop making fetch happen. I'm trying to make morphometrics happen because it's a biology term that actually says like this is what how you describe something complicated like morphology into some couple of simple numbers. And so like I want to do that for H1. And so the idea here is, hey, our PSF or beam for radio astronomy is typically bigger, so we have fuzzier image, but because we can follow the hydrogen throughout the whole galaxy, we can actually get roughly the same amount of information. And so I can get about the same quality of morphology information, but it's different because stars have the dynamical range of the image. The central bit here is like 1 million or more times brighter than the outskirts of the stellar component. But for the H1, you have maybe an order of magnitude of range, like not even. They're all sort of the same brightness. So you have different, the morphometrics work differently. So I use concentration, asymmetry, smoothness. I always throw up this slide because that's where I got them from. But it basically tells you how concentrated the light is, how symmetric, asymmetry, and smoothness is something I try to ignore as hard as I can. But you flip the image and then you compare the difference, or you smooth the image and then compare the difference. I use the Gini index. So if you are familiar with any of the work of the United Nations, for example, the Gini index is to show how income equality is working in a group of people. So we could do this here, but it's too depressing to start sharing, annual revenue.
The US
So
is probably close to 1, right?
no, so so the whole idea is like if everybody has an equal share, so if I go along the fraction of pixels there, and every pixel has an equal share of the photons, you basically follow that line of unity. But if you just start diverging from it, so basically all the photons sitting in the last one, and if nothing else gets any information. So you essentially, Gini is 0, Gini is 1, that's sort of the extremes. And so if you have a population and you start approaching 1, that means all the wealth or all the photons are sitting in one item. So I can think of it as like Gini of 0 is the Smurfs, everybody's sharing everything equally, perfect communism. And in the case of Gini is 1, you've elected a royal, and all the money's over there now. This is not a political statement. This is what you end up with. Both of them are blue people. And the other one is, the last one is that there's a way to do M20 to actually find morphology. And we're still actually coming up with new morphometrics. And as you can imagine, these things are not actually span a orthogonal space, right? If I increase my concentration, if I have a my Gini index also changes. But this is sort of what we came up with, and it sort of spans things. It doesn't have a fantastic way to identify subtle stuff, so that's what we were hoping. Maybe we can actually, because honestly, this is as all good science projects start as an exercise in laziness, because we didn't want to look at everything all the time and then just rely on somebody's eyeballing things. One single person. It's much more fun to do that with like a group of people like Galaxy Zoo. But so we looked at a couple of this stuff, and subtle things like lopsidedness is still hard to find. And then I tried this out. And so 3 years ago, I talked about this first image that we got with ASCAP about the Hydra cluster, and I tried to separate things out that were currently undergoing dynamical friction, undergoing tidal forces, merging. They were in a state of transition. That's what I was after. Didn't work fantastic. It sort of worked, just enough for me to go, well, it ain't broke completely, but we need some better data, and I need a bigger data set to try that on. So, hey, train your machines. And so you need a good data set to train on. If you do any kind of machine learning, this is almost an axiom that any machine learning person will tell you. Look, if I have a great data set where every possible use case is properly represented, I can do that, on much bigger data sets, because, hey, I can train on that. That's not the problem. The problem is always, how do I get my data sets to train on? And so in this case, we had 2 galaxy groups, and here in the center of that, Lin et al. Identified using a holistic approach, so using both ASCAP, but also the FAST radio telescope, and optical images to sort of say, like, okay, those are perturbed, those are undergoing merging, ram pressure stripping, some sort of transitional thing is happening there, and those are not. So in the green line, I sort of have my my training set, but anybody who knows machine learning goes, that's still not a big training set, right? It's still on the smallish side. But Wallaby will be doing, this is pilot data, so Wallaby will be doing many more groups and much larger parts of the sky. So I thought, hey, can we identify these perturbed galaxies? So how do you do that? Well, your classification based on nearest neighbor. So if you don't know what you need to do, you go and ask your neighbor, and your neighbor will happily say, that's the plumber you should avoid, and that's the one you should go for. And in machine learning terms, that basically means if you have a multidimensional space, and it doesn't have to be orthogonal, which is great, you just go, what are, including in the Euclidean space sense, the closest examples in my training set. So you go like, I'm going to take the average of, those 5 surrounding my target, and it's like, okay, the majority says green, and then it becomes green. But if I say the majority 3, then it becomes red. So the big choice is how many neighbors do you ask, right? And so that's the trick. And so it depends on how dense your training data set is spanning that space as well. Just to give you an idea that I've been using recently, so you can go in a color space, for example, and just take the average and see what that classification is. So you can turn a color into a classification of a stellar type that way. Here's a bit about, where I start to talk more machine learning time of phrase, which is like accuracy, precision, recall, and F1, which are all measures of how well am I doing, how well am I, how clean is the sample that I'm selecting, how clean is the sample that, how well do I retrieve my sample, that's the recall part. And so you try to get them all in the high end of the percentage, so you're all trying to get like close to 100% accuracy. And precision and recall. And as you can see, they sort of diverge as I add more neighbors to it. So it comes down to how many neighbors do I use? About 2 seem to be a good compromise. That makes me a little nervous because if it's 1, you're literally asking 1 person, and nobody should go with the plumber when they've asked that 1 neighbor. That might just be a person who's the plumber's cousin or something, right? So there's a risk of higher variance and basically overfitting when you do that. So I just threw everything at the wall and tried to, with my training and test sample, sort of went through every accuracy and precision and recall, like all of them, but with all combinations of how many. How big a feature space, like how many different features do I use and how many neighbors do I use and what's a good result. And so 2 seems to be definitely working. So if I do that, I get, this is called a confusion matrix, which I like because, it has the word confusion, so everybody can feel confused. So you have a predicted label. I say like yes or no, it's not interacting. Yes, it's looking perturbed. And then I look at my actual, so I look at the envelope like, okay, was it actually accurate? It got it right, the majority of the time. I'm already like, not too bad. But there's still some on the off axis. It's okay. And, but, not amazeballs, but a lot solid, lots more solid. 85% is pretty good for something as fuzzy as morphology. So I'm pretty happy with this. It's getting better, but then I was like, all right, we have 1 more group that we have and that we don't have those labels on. So I can now predict using my KNN which one of those group members is perturbed and which ones are not. And then when somebody does the study like Lynn did, a year ago, they can just literally look at my list and look at their list and compare later. So I can make a prediction with this. So let's try that out, right? So that seems to be working. And then I had just, did I get the fraction right? And the KNN seems to get the fractions for these things pretty solid. So as a group, it's pretty good. Individually, 85% chance of success. So your mileage may vary a little bit. But how does it look as a group? And like, how did the scaling relation? So stellar mass versus star formation rate, do you retrieve those? Things like stellar mass versus H1 mass. And so do the same trend hold in the training sample as it does in the actual deployment sample, as I call it now. And really what we're hoping to do is deploy this on all of Wallaby, which is currently underway. So I can then look at these things and go, hey, if you're perturbed, for example, you have a much flatter relation between stellar mass and H1 mass. So basically, if you're a big galaxy, you're relatively speaking, you're sort of lost a bit of H1. That seems to make sense. All right. Then I tried to do the baryonic Jolly-Fisher relation. I don't know, not sure what came out of that. It seems they all seem to be agreeing. And in my training sample, it seems to be much flatter, so it's unclear what's happening there. So yeah, training set's still small. A reasonable way to identify perturbed galaxy. Definitely a good way to do it if you have a group and say like 20% of these are perturbed. Individually, it's a weather forecast, so it's like 85% accurate, which is fine. But it's straightforward to deploy, right? This is the kind of thing, and it also told me which morphometrics were good to use, like where is actually the information sitting in. So there's things like, oh, I can get rid of that one. And so all of these was a very good, useful thing. Why did I talk so fast? Is because this was my first talk, and I was going to talk the other bit, which is about the planetarium, which I promised yesterday. So one of the things is Python is freaking awesome. You should all know this by now. And one of the things that I was like, I would like to learn how to make maps in Python. I love maps. GIS data is free because a whole bunch of people have just been measuring everything. And so you can get the GIS data. This is the GIS data of Louisville. And so this is every street in Louisville, and you could just plot that up. But because I'm not happy with that, I made a movie of the whole thing. So this is Louisville. Okay, where did the students come from? We start in on the 17th of August, 2012. Let's get started. And this tells you where the school visit came from, and sort of you have your cumulative number of students at the bottom. And very dramatically, it ends, you know, almost 4 years ago for obvious reasons. But it should tell you, you know, it didn't. I got this as a giant table, and giant tables, you cannot convince people with giant tables. If I ever give a talk, it's like I try to avoid tables or I skip over tables. Nobody ever, you put everybody to sleep. Equations and tables, don't use them. And so, not in talks, right? And especially if you want to convince. So look, everywhere, these students were coming from everywhere. And you know, look at the numbers of students that visited cumulatively. Then I like to do visuals like others, where it's like, okay, I figured out how to make the size of the point relative to the size of the group that visited. And as you can see, we pretty much blanket Louisville, and there are groups going from further afield. I was like, well, it seems to be even further afield. My little GIS map of Louisville is not good enough, so I made another movie. And so you can figure out where Louisville is, because that's where all the points are happening. But actually, we have like several counties worth around us where a lot of these students are coming from. Like some are pretty far afield, actually. Like that's a sizable field trip. So this sort of gives you an immediate idea. Like everybody, hopefully in the room, gets a feeling for like, this is where our students are coming from. This is how many students are coming, and this is, you know, our reach. So this is my my immediate knee-jerk reaction is like, I must convince somebody. I must make a data visualization, as if, you know, everyone is convinced by the data visualizations, but at least you get maybe half the room with you if you go like, look, this is important. So, sorry, I'll go to this one first. So, hey, I put in a change.org. You may have all seen it, because I think half of you are friends with me on Facebook, but did that, made a drawing of the Reich Planetarium. We're trying to convince people to, well, we're trying to get a nice big tally. We're over 2,000 votes already, so yay. We'll see how much I can boost that. And so we'll see if we can, between the data visualizations and the voting, we can convince people to fund our planetarium. The last thing I want to do is, there's the exploration of astronomy for Kentucky students, Oaks, because I really wanted to make this, you know, horse race related. And so this is the site where it's at, but that QR code gets you there as well. It's for students from Kentucky to work with, mostly we have projects from professors here in Kentucky, but it is a REU. It is to support you to do these things. So you will get paid to do research. It's your little job now. Well, I don't want to say little job, it's actually a pretty decent pay. And we can get you to the American Astronomical Society meeting. We have a couple other ways to support you. And so you can either pick one of those, or if you go, hey, I really wanted to go to that out-of-state REU, but I got rejected, then you know, apply for the Oaks program, because we're happy to support you to go to your dream REU. If this is like, I really, really, really wanted to go to, well, I'm not sure if Puerto Rico does one right now, but let's say Puerto Rico, I really wanted to go there. apply here, and we're happy to see if you can support you, or do one of the projects with our participating professors. Apply by April 8th, please, and so here's your, the form is on the website, under the student, component.
You should maybe put this on the KDE, but.
Yes, that's where it's going next. I mean, I literally finished this before we got here. So this is blasted out to everybody. And the idea is that we help Kentucky students actually do some research and do it a little longer term, not just for a summer. This is a sort of a year-long project, year-long support. So I wanted to advertise that here and everywhere. So thank you.
Any questions on any of this talks?
Sorry for the 3 talks in one. I can give a 4th one. Yeah.
So one on that is, with the concentration, Gini index, all those kinds of ways of measuring perturbedness, interaction. I'd taken a look at Jen Lotz's paper back some years ago, was trying to do it
2004,
myself.
2010, yep. Yeah, so I know those, yeah.
And the, one thing that I wasn't sure about was, is it possible some way to use, to identify kind of a number on that from somebody else's set that you could apply to yours, or do you really have to customize it for your redshift, wavelength, telescope,
Yeah.
steaming conditions?
Yep. So this is we went through an exercise with H1 because again, it's, not as much of the range of dynamic range. So the only differences are beam sizes really.
Okay.
And Adam Reynolds did this 2020. He went through 3 different surveys and it was just asymmetry and it was a horror show. It's just the kind of thing like you're better off doing this within the same survey because you're sensitive to the same surface brightness, same resolution, same wavelength regime. These things were often sort of touted that, you know, you're fine doing this as long as it's a star formation band or it's, you know, roughly the same redshift. But I would say that the subtleties really creep in.
Okay.
And so, yes, it works within the survey, within the wavelength, within it. But as soon as you go to, you know, you want to compare redshift 0 to redshift 5, there's too many resolution.
So kind of like Alan was saying with these large surveys, it's calibrated but not standardized in a way.
Is it the other
within
way
your
around?
survey-
It's standardized, but it's not calibrated. It's something like that, right? It's not, it's.
Within your survey, you can get results, but you can't necessarily compare to other people's numbers that they've got.
Yes, it's ordinal, but it's not, whatever the next data thing is, which is like, it has a 0 point, right? So if I can say these things are more asymmetric than the other.
Okay, you got a ranking.
Right, I got a ranking that way. And
but
so
you don't
that's why.
have zero.
Right, that's why I think within these things I like labeling things this way so that you can get like, okay, I know the technique that I can use. So with machine learning, this is called transfer learning. If you have learned something on one data set and you've got something that is similar, right? So if you've trained on the Galaxy Zoo classification of Sloan Digital Sky Survey, for example. Fantastic, wonderful. But now LSST comes along, and actually LSST is a different telescope, it's deeper, etc. Okay, but it's still the same colors and rough redshift range, so I can transfer learn. I don't actually have to relearn the whole thing. So I know the techniques to do it, and I know that like if it's a convolutional neural network or something, I don't have to do the first 5 steps. Those can still be the same. I just have to train on the last bit. So yeah, transfer learning this is part of the reason why I was doing this, because I was curious if this was a good space, because this already steps it down from images down to a smaller set of numbers, right? How do you get to a feasible number of things to train or to classify? That's part of it. This was the exploratory phase is now concluded. I now know which parameters to use, how to use them. Yeah, so that was useful, but within the same survey, it's very frustrating.
We do have an online question
Yeah.
from Austin Hinkle. He asks, can you pass in the redshift or survey as an additional feature?
Right, so this is the other thing that you then do. The problem is that if you're at a different redshift, you are also with a different instrument. And the instrument is really the thing that changes it. Like you can do it with the same, you can sort of match wavelengths with Redshift. So you can go like, okay, my SESZ band is the equivalent to SESG if at Redshift 1, for example, or 0.8. So I can use those two, but then I also have the Redshift and resolution effects, and the resolution effect is the biggest one. If I smooth the hell out of the whole thing, I mean, everything is no longer concentrated. So, yeah. So the distances, and with the H1, the distances turned out to be the big change. So it's like I can do it in a very local universe. So, yeah.
Any other questions? Yeah.
Yeah.
So on your planetarium map, you listed Louisville and
Nope.
Would, yeah. Would it be helpful, maybe, I mean, could you have color codes of like the areas that where you have your underrepresented, you know, or
Oh, that's,
underreached?
so if you're in, yeah, so I just use green points because I like green. I was getting to the color coding.
Yeah.
So we have public schools, private schools, mostly Catholic schools, churches, and other. So I could have 4 colors of the different people, of the different groups that came in with students. So these all come with like, they're counted as long as it's a group of students. So it's like, it's the church group, or it's the Sunday school, whatever, you know, it's, so I was gonna label it like that. If you wanna do underrepresented, it's quite easy. You take this big road here and this big road here, and anybody in that corner is basically underrepresented.
Yeah, I was like the background map.
No, so
Yeah.
the background map is, you could, but honestly, if you're familiar with Louisville, you know where people who are in,
Sure.
live. But here's the thing, it nicely shows that we have, it's not just, you know, JCPS on the west side has come to our planetarium. We actually serve everybody. And that's really what this is trying to convey. We served everybody in every year. And so that's the plan. I do feel like, I think a few of these things are portable planetarium versus planetarium visits. But I think the best way to do is like to show like, look, we have our entire catchment area of the people that we are trying to get to go to the University of Louisville. They're visiting our planetarium.
Otherwise, send them to us. Right? Send them to us.
You're about to steal our lunch there, yes.
Exactly.
Well, I would love to hear your numbers and where they're coming from, because you can do the same thing. But then, for example, link the number of students visiting to the number of STEM students you have. Right, that's another thing that I'm looking at. And as far as I can tell, of course, the pandemic threw a curveball in everybody's plans. So your mileage may vary, but we do seem to be missing STEM majors. So, and a fair number of them. So that,
because they don't get introduced, right?
the idea doesn't get planted. If you take people in 6th grade and they go to the planetarium, that idea is going to rattle around there for a few years, and then they're going to go like, that might be a major. Maybe not astronomy. I know, like they told me in 101 class, like, I'm not trying to turn all of you into astronomers. I don't like that amount of competition. So it's my point is that, you know, the idea of like, hey, I could go here, I could do geology, I could do something in science, is very much an option. So yeah, I've been trying to visualize our numbers rather than show a table, because I've never convinced anyone with a table.
Yeah.
I have a table in this talk, but nobody noticed, I think. So yeah.
Well, I have a table in my talk, so that'll be great.
Sorry.
Visualization.
Yeah, any other questions? Any of the 3? Yeah, so I'll post those QR codes and things on the websites. And so.
All right, thank you.
Yay. How do I get out of here? Okay.
And I will not introduce our next speaker, because I'll introduce myself in a second, so.
Help.
Yeah, just click escape.
Oh, right.
Yeah,
the button that does it all.
Make Close your thing and,
Okay.
file and just use this all. There's still on.
Yeah, still sharing.
Yeah, come on.
Unfortunately, I can't, can I see it up there? Where's, no.
Yeah,
Is that, which one slideshow?
you go on the bottom.
I can do that too.
Just hit F5.
Yeah, just down there, a little bit over, no, too far.
And maybe
There we
I'll-
go. I see
Got
it.
it?
Yeah, there we go.
Nice picture.
It's like, I can't read the bar. Anyways, so, okay. My name's Kyle Cook. I'm with University of Louisville with Dr. Halvera, who just finished speaking. And I'm talking on detections of UV bright galaxies in the initial Laduma L-band data. If you have been here the last couple of years, you have heard me speak of Laduma, but not everybody may have. So kind of the quick recap on the Laduma survey. This is a radio array, the Meerkat array, in South Africa. That is the precursor instrument for the square kilometer array. So we are kind of Laduma is a study working on Meerkat, kind of as like proof of concept of what this instrument is capable of. And the intent, as Bene talked about with H1 and the 21 centimeter line, is to get the deepest direct detections of H1 that we have ever had, because H1, the 21 centimeter feature, is notoriously faint, so it's quite hard to detect. And our best efforts to get deep have been like heavily stacked data. We're going for direct detections out to a redshift of about 1.4. So that will be the ultra high frequency band, which is not the data I am working with right now. I'm using the L-band data that is all pretty local stuff, but the further stuff will be coming in later. One of the other things is the Laduma's goal of kind of galaxies is to get Milky Way sized galaxies out to about a redshift of 1. So we can get pretty good as we go further out as well. So what I am trying to do with that is take that initial L-band data, which goes out to a redshift of about 0.08. So like I said, comparatively quite local. And combine it with a lot of other data sets that we'll talk about in a second, with the intent to try and see if we can identify any information on whether a galaxy may be rejuvenating or quenching. So just kind of the quick recap there. Galaxies kind of have a life cycle with star formation. And ultimately, we're wanting to understand that relation between the stellar mass and the star formation rate. So with this in particular, can I look and see galaxies that we can identify as potentially turning off their star formation, or maybe even some that are starting to turn back on? So that's kind of the focus here. Quick look at the data set. So the Laduma data is the new piece. Okay, everything else is existing data. The Laduma data is the new one, and it is direct detections of 227 galaxies in the Chandra Deep Field South. And like I said, that's out to about a redshift of 0.08. Zoo catalog came out late 2022. And we're using that for SED fits of a large sample of galaxies, let's just say 800,000 sources. It does overlap our field. They are not exact overlaps, right? So we're not necessarily have the same field of view of everything. But one thing in particular with Zoo is, well, actually one used Seagal, which anybody who's done SED fitting codes, one of the complaints about Seagal is the star formation history, and that you're kind of locked into that tau model and you can't really model other options in there. But the UV information also comes from Galix, which is fine, but we want to kind of try to incorporate Swift data. So instead of the broadband Galix filters, we can go to the more narrow band Swift filters and see if we can kind of tease out any information having that information as well. So we have Swift data, about 1,100 sources from that. We do also have a similar data set from XMM Newton's optical monitor, though we are kind of defaulting to the Swift data. And that leads us into, oh, forgot that little bit. So after all these catalogs are matched together, so the final catalog that has data from every single one of those, with the exception of the UV data, I will say either UV data with zoo data with Laduma data. We get 7 sources from Swift, and we actually got 8 sources from XMM, but most of them are repeats. And then some don't actually have a complete set of ultraviolet data. So maybe we just have a detection in the M2 filter or something, but we don't have the other filters. So after those are removed, we get 1 unique detection from the optical monitor. And this is our first plot. So these are our fun guys. These are our 8 sources over here, which always show up not as great on projectors as they do on computer screens. Especially number 3 right there, which you can probably barely see, super little faint guy in there. But it's an interesting set. I think 2 is one of my personal favorites because we have checked and it is an interacting galaxy pair there, so that's fun. But we have kind of the star formation main sequence. The dashed line on there is just the cutoff for the upper limit cutoff for the Green Valley. So everything's numbered. You kind of see sources 3, 5, and 6 over here, which are really faint, diffuse. They do have actually the bluest UV colors. So the color on here is the ultraviolet color, in particular W2 minus W1 color. So our faintest things are our bluest things. And then we have 1 galaxy kind of floating down here in the Green Valley. But we do have a nice spread in masses. In particular, all the UV colors are fairly similar. But we also look at the gas fraction. So we look at this in terms of the gas fraction, burst stellar mass. The black points come from paper by Drabala, and just kind of comparing to this trend. So one thing we notice in particular is if you look at sources 1 and 4, those down there are kind of on the low end of that trend. So overall low gas fraction. So by gas fraction, I'm meaning H1 mass compared to the stellar mass. So low H1 mass compared to the overall mass of the galaxy. And again, we've got a nice spread. We've got a few different points in a few different places to look in here. So 8, 2, and 7 are fairly high on that trend. And this is where I have my table. I apologize, trying to summarize those 2 plots into trying to make a reasonable thought from this. So yes, I did not include numbers. If you want numbers, I do have a slide with numbers, but just kind of a qualitative statement here. Most of the sources are relatively green, UV green, but the 3 low mass are actually quite blue. Everything is within the star forming main sequence, except our last source, which is the one that came from XMM. And it is sitting in the Green Valley. Just kind of a general statement about masses and their gas fraction, and kind of trying to pull all that together into a consistent picture. You notice I've got a couple marked rejuvenation. So these are in particular are things that are sitting on top of that relationship there. So they still have a fair amount of mass. And when we look at this guy in particular, he's sitting in the Green Valley, but having a large amount of gas. So he still has a lot of potential to form stars. And while I did say the UV colors are all pretty similar, you also have to think this is by definition a UV selected sample. So all these things are relatively bright in the UV, right? So they're all kind of up in that star formation. And if we even go back to this, you notice our quiescent population is quite sparse, right? So that's just kind of disappeared because we selected for star formation. So pretty much star forming thing in the Green Valley, but has a high amount of gas. We're interpreting that as moving up into the star formation and rejuvenating its star formation. On the other hand, you have things like source 1, which again is kind of that green UV color, but it is I don't know, kind of in that mid-range, but it's a low gas fraction, or sorry, low mass, but has a low gas fraction overall. So we're kind of seeing that probably dropping down towards the Green Valley if we kind of try and picture our main sequence as a moving timescale picture. So long story short, we have detected what looks to be a sample that contains both rejuvenating and quenching galaxies to kind of start mapping out that, like I said, that relationship between the star formation and the H1 mass over time. So, and if you do want numbers, there you go.
There we go.
I was just trying to keep it a little bit cleaner, but yeah. So I will take any questions that you have. Yes.
So I have all the UVOT data. Are you using a single observation or are you merging them together?
So we are using pre-existing data. So we did not actually reduce that at all. So it was it's kind of an interesting, it's data from Leah Hagen that was then reprocessed by I don't know if it was one of her grad students, but Nagaraj is his last name. So, but it's initially Leah Hagen's data, if you're familiar with her work and how, but yeah.
I know Leah from when I was at Penn State.
Yeah. But that's the source of the UVOT
Okay,
data.
so she merged them probably already. Right?
Yeah. Yeah, we're just using the output catalog from hers.
Okay, all right.
Yep.
Mhm.
Okay. Anybody else or anybody online?
I don't see anything online right now.
Yes.
We do have a couple of really red and dead galaxies, and they're detected in the UV.
Yeah.
Any idea what that is?
Oh, if they're red, maybe you're dealing with the red link in the W1 filter.
No, I mean, they're UV detected.
Yeah, that's what I mean. There's a red link in the W1 filter which goes into the optical.
Oh, so they're just bright.
It's just well, it could be if they're bright in the optical, then you get some photons in the optical in the UV W1 filter, which you think is coming from W1, but there's a red link. The filter is very broad.
Yeah. I mean, I think.
I mean, if you don't see it, I would always look at the M2 filter because the M2 filter is really narrow band and it's very sharp.
Yeah, one of the reasons, if you notice, I only really showed W2 minus W1 is because if we do, so if you think in terms of filters, blue, green, red, you've got W2, M2, M1, or W1.
Yeah.
When there is a very, very stark difference between the overall colors looking at W2 and M minus M2 and M2 minus M1.
Yeah.
And right now I'm thinking that part of that is because the 2175 angstrom bump sits right in at a redshift and sits right in M2.
Correct.
So we're kind of getting this artificial flux in M2 that I expect is probably quite throwing off some of the values
And
there.
it's coming from calibration, right? It's not,
Yeah.
not real,
Yeah. So at this point, I've kind of pulled back from using M2 for anything.
No, it's would
Because-
be only a double check basically. If
Yeah.
you don't see it in M2, but you see it right in W1, that might actually tell you that this is not real ultraviolet emission. This is optical emission that leaks through the filter.
Yeah.
Through the filter function.
Yeah, ultimately, the Swift data that I ended up with, I have data for each filter. So I have every source on that plot is detected in all three. But then looking at the colors individually, I have those plots. I don't have them in the talk. They are on my computer. So we can look at them later if you want and kind of see the color differences in there. Okay. All right. Thank you very much.
So I guess I can stop the recording, right?
Okay, so for lunch, we got lunch tickets here.
Can we leave our stuff here?
You could, I don't expect any trouble, we really don't have, that's on campus, but if you do worry about it, I can just lock it up in the planetarium right next door.
Okay, let's do that. One thing should we get, I stopped the recording now. I see you at 1.